In this video, we're going to look at finding the volume of a solid by slicing. So we're given the base of a solid is the region bounded by y equals 1 minus x squared in the x-axis. And we're going to take cross sections perpendicular to the y-axis, and we're told that those cross sections are squares. All right, so this first graph on the left is giving us the graph of our region that is the base. All right, so we're going to slice this way, perpendicular to the y-axis, and then we know that the cross sections when we slice it are squares. So in this case, if we look at, here's what a picture of what the solid would look like. So here is at the bottom our base of our solid. Notice that when we slice perpendicularly to the y-axis, the green line here is representing your y-axis. When we slice perpendicularly to the y-axis, we get these squares. So here's another picture of just what a representative square would look like. So here's that parabola 1 minus x squared. You see it really well down here in this picture. And we have squares here. Now our scale makes it look a little bit like it's a rectangle. It really, in this case, we really do have a square. All right, so when we want to find the volume of a solid in this fashion, we were to take the volume of a representative slice and add them all up, and recognize that we have a Riemann sum, so that when we take a limit, we get an integral. So really, what we're going to do is we're going to integrate an area and give us a volume. All right? So I need to know what is the area of this square at a particular slice. Okay, first, since we're slicing perpendicularly with slicing perpendicular to the y-axis, we have to integrate with respect to y. If we're integrating with respect to y, we need functions of y. So the first thing I'm doing is solving our right curve and our left curve in terms of y. So solve for x, you would subtract y, add x squared, and take the square root. When we take the square root, we get a plus or a minus. So the right-hand side would be your positive root 1 minus y. Your left-hand side would be your negative root 1 minus y. The distance across here is what's giving us the bottom of our square. So to find the distance across, we're just going to do right minus left. So we're going to do root 1 minus y minus the negative of root 1 minus y. So that's just the length of the side of the square. To find the area of a square, we square a side length. So we'll take that side length and square it, multiply it by its thickness. That gives us our volume of a slice. And then integrating adds all of those volumes up. Okay, so that's where everything's coming from. This is the right curve in terms of y. This is the left the left curve in terms of y. Subtracting the two gives us the length of the side of the square. Squaring it gives us the area of the square, and then multiplying it by the thickness gives us the volume of that cross section, and the integration adds everything up. Now again, we're integrating with respect to y, so absolutely everything has to be in terms of y, including the limits of integration. So our limits of integration here go from your lowest y to your highest y, so it goes from 0 to 1. So I have the integral from 0 to 1 of 2 root 1 minus y quantity squared dy. Squaring gives us 4 times 1 minus y, go from 0 to 1. Take an antiderivative here. You could antidifferentiate piece by piece, or you could do a u substitution on this 1 minus y, which is what I did. Plugging in the endpoints and simplifying gives you a volume of 2.